Welcome to the first video of the class of the transfer phenomena. Basically, this first video is going to be about some basic concept. Basically, we can call this introduction or overview. In this course, I'm gonna try to utilize the book of the transfer phenomena, second edition by Bird and Stewart and Lightfoot. In this video, I'm gonna introduce to you this book and basically what is inside of this book and how we are gonna utilize all this information inside of this book and what is the organization basically, because to know the organization is very well and what is actually inside of this book later during this course and after this course in our rest of life in research or other fields, we can go and we can read and we can find what we need in basically encounter any problem in our life. So the first things I want to introduce the parts and the chapters in each parts. The first is chapter 0 is the introduction. Basically give some definition what are transfer phenomena, why we study transfer phenomena and so on. In the first part we call this momentum transport. It's called started by a first chapter, then define the viscosity and the mechanism of the momentum transport, and we can find all those subtitles. And in the second chapter it gives some information about the shell momentum balances and velocity distribution in the laminar flow. In chapter 3, the equation of change for isothermal systems for continuity situation. And in chapter 4, we call it velocity distribution with more than one independent variables. Let's say inside your system, let's say you try to model and measure the temperature with respect to different coordinates, let's say is x, y, z, or respect to time. That's why we call more than one independent variable. Then chapter 5, we call it velocity distribution in turbulent flow. And chapter 6, interface transport in isothermal system. Chapter 7 is macroscopic balances for isothermal flow system. We know there are 3 levels, and microscopic balance, microscopic level, and a molecular level. In here, it gives some basic overview and basic definition and derivation of the macroscopic balance for the isothermal flow system. And chapter 8 is polymeric liquids and so on. In the second part of this book, we'll see energy transport after momentum transport. In the energy transport part, in the first chapter, start by chapter 9, let's give some definition of thermal conductivity and the mechanism of the energy transport. And chapter 10 is give similar to first part, momentum part, give shell energy balances and temperature distribution in solids and laminar flow. Chapter 11, the equation of change for non-isothermal system, again non-continuum scale, continuum situation. Chapter 12 is give temperature distribution with more than one independent variable. Chapter 13 is temperature distribution in turbulent flow. And chapter 14, interface transport in non-isothermal systems. And chapter 15, again, macroscopic balances for non-isothermal system for macro level. Again, chapter 16 and the final chapter in this part, energy transport by radiation. And the final part of this book is give the mass transport, and it start by the chapter 17 in definition of the diffusivity and mechanism of the mass transport, and chapter 18 concentration distribution in solids and laminar flow, chapter 19 equation of change for multi-component systems, and chapter 20 concentration distribution with more than one independent variable, and chapter 21 concentration distribution in turbulent flow, chapter 22 interface transport in non-isothermal mixtures, and chapter 23, macroscopic balances for multi-component system, and final chapter in this book and this part is other mechanism for mass transport. We are gonna, this book is study. Actually, what is gonna be this class organization? First of all, I'm gonna in this video give some introduction, basic concepts of transfer phenomena, and in the following videos I'm gonna go over some mathematical concepts. We need to understand physical concepts and the derivation of the mathematical formulas and to model the systems in this course. And the following other video I'm gonna try to give some overview of the vector and tensors and go and analyze them, and then start the chapter inside of this book chapter by chapter and go over all each chapter and try to mention what are the important part of this in this book, for what are the important equations and the statements and the paragraphs to give you, basically to summarize, and so and go on like this and try to finish all this chapters in order, basically. So when we continue, so in the first chapter 0, basically what are the transfer phenomena, and the subject of transfer phenomena study three topics together simultaneously. The first one is the fluid dynamics. It's related to momentum. The second one is the heat transfer, and the third one is the mass transfer. Basically, fluid dynamics involves the transport of momentum, and heat transfer deals with the transport of energy, and mass transfer is concerned with the transport of mass of various chemical species. Why the transport phenomena study of these three together? There are some main reasons. The first reason, we can say, if we go industry and biological, agricultural, and other fields and other science field or engineering fields, we'll see all these three events: momentum, mass, and energy transport events happens simultaneously together. This is the first reason. And second reason, the basic equation that describe all these three transport phenomena, mass, momentum, energy, they are closely related each other. We call this concept analogy. The other reason, the mathematical tools needed in this course to understand the basic physical phenomena uses are very similar each other. The other one, the final one, the molecular mechanism underlying the various transfer phenomena are very related, close to each other. And because of these four reasons, this book studied these three phenomena together: mass, momentum, and energy. And basically, as I said before, there are three levels the transport of phenomena involve. The first one is the macroscopic level. In this level, the set of equations is called macroscopic balances, describe and derive for the mass, momentum, energy, angular momentum for any system be described by the control volume and control surface and interaction between itself and its surroundings. In the second level, we call microscopic level, as examine the fluid mixture in small region within the equipment. We write down the set of equation called this type of equation of change, and it describes how the mass, momentum, energy, angular momentum change within the small region, smaller than the macroscopic level. In the molecular level, this book seeks the fundamental understanding of the mechanism of the mass, momentum, energy, and angular momentum transport in terms of molecular structure and intermolecular forces. Basically, if you go for this three level uh, different levels. There are different length scales. For example, if you go to industry, any industry problem at the macroscopic level, the dimension of the flow system may be the order of the centimeter or meters. But if you go in the smaller region, smaller level, is macroscopic level, it involves in the system in micron and centimeter range. But for the molecular level, it involves 1 to 1000 nanometers. Describe all three different levels, how they are big. So if you go continue, in this course, basically what we are gonna do, first of all, we will define the system and try to derive the conservation law for any system. For example, is continuous issue of the scalar. The first scale, as we said before in the transfer phenomena book, start with the molecular scale, then we move to nanoscale, then we can move to the continuum scale. So what is the continuum scale basically? It's characterized by the materials that have properties that can be described by the continuous function of the time and position. We can describe this system by the continuous function of the time and position. Also, the derivatives exist and are continuous as many as we need. We call this continuum scale. What are the properties in this continuum scale? We can give as an example. The first, density, temperature, pressure, enthalpy, entropy, internal energy, and velocity, acceleration, and so on. We can give all this example of the properties of the continuum scale. Basically, what it's trying to say, let's take the temperature. Let's say we define our system. We have some control volume, control surface, and we know interaction between its surroundings. And we can describe this temperature by some continuous function of time and position, because this inside of our system, the temperature can change respect the position and the time. So we should have some function describe how temperature of inside of system change respect the position and the time. Also, this functions some derivative should be exist, and there should be continuous as many as we need. Then under this condition, we call any system is as a continuous system, continuum scale. We can describe this later on. So after basically this continuum scale is collection of the infinitesimal very small systems. These systems, very small system has very small mass and very small of the volumes. The collection of these small systems give this continuum system. So if we move the next level, collection of this continuum scale, when we scale up this system, we can get some unit operation, let's say like reactor and separation system. And after that, the collection of the unit operation gives us the plant scale. Actually, conservation laws. For any system, we can derive some laws. We call this conservation laws. This conservation laws is related to mass, total or elements, or energy, total and other type of energy, kinetic, potential, mechanic, or others, and momentum, and charge, and angular momentum. So definition of conservation. What is conservation? A conserved property is neither generated nor consumed. Let's say, take some example, let's say energy or mass. According to this definition of the conservation, we cannot generate mass and we cannot consume the mass or energy as constant. We go in the next part, but how about the entropy? Entropy is not conserved. We know the entropy can only be generated; it cannot be consumed. We know from the thermodynamics courses. and the second law of the thermodynamics. Entropy only can be generated, cannot be consumed. For the isolated system, entropy can increase until they reach the equilibrium. When the system reaches the equilibrium, entropy's generation is reached to zero. So on. So in the next level, the review of some macroscopic laws in the undergrad course in the modeling, especially in let's say in chemical engineering modeling, we'll see when we consider any system. Let's say in here the system boundaries and system control volume and the control surface. Let's say system has some volume and some of the density. Let's say system has some inlet and some outlet. This inlet is m dot is in kilogram per second per time, or m dot out is kilogram mass per time. Actually, conceptual statement we know from the undergrad course, the accumulation rate of mass in the system is equal mass input rate and minus mass output rate. It's give this general conceptual statement on what's happening inside of this system, basically for by the inlet and outlet and accumulation terms. This is the statement, conceptual statement. When we explain this conceptual statement by the mathematical formula, by the symbols, we say d over dt rho v is equal m dot in minus m dot out. Basically, this rho is kilogram per time. Is this v is represent the volume. It should give us kilogram per kilogram per meter cube. Let's say this, let's so call this meter cube is then we should obtain is mass per time, and we have the mass per time. So for the continuum, we obtain from here this is the for microscopic case, but for the continuum macroscopic case, we will get this type of mathematical equation. We call this Dal operator. I will define this later, go overview. And this is the difference between two levels. Basically, we call this the internal equation, internal mass balance. We call this differential mass balance, and we call this the continuum. So conservation of the energy, let's say we have some process, and this is the system boundary. There is some mass inlet and there is some mass outlet. There is some internal energy and enthalpy in. There is some internal energy out, enthalpy out. Because of the velocity of the mass, we have some kinetic energy, and because of the gravity, we have some potential energy. And these are in and these are out. Basically, we give some Q dot some heat to the system, and we give some W dot some work in the system. And what is the conceptual statement of this process for in terms of energy? We call this accumulation rate of energy in the system, inside of system, is equal to energy input rate, all this combination, collection of this all different parts of energy, minus energy output rate. If we translate this conceptual statement to mathematical symbols, we say d over dt is system energy of the system is equal to internal energy plus kinetic energy plus potential energy multiplied by the inlet mass minus again inlet energy and kinetic energy, potential energy plus multiplied by m out and plus q and q dot plus w dot. We know this from the undergrad course. Actually, we call this macroscopic equation balance for this our system. But and if we translate this enthalpy, we can write like this. If we try the enthalpy is u plus pv, then we can write the enthalpy in here. And this is the conservation of energy actually. But in this course, we are gonna deal with the continuum level for differential equations actually. Another example, conservation of the linear momentum. let's say we have some system body and system boundaries and some mass in, and this mass has some velocity, some mass out has some velocity, and the forces acting on the system boundaries, what is the F1, F2 and F3. And if we say the general statement of the conservation of linear momentum, accumulation of the rate of linear momentum is equal to linear momentum input rate minus similar to others and output rate. A symbolic statement of the macroscopic system, we have this linear momentum symbolic representation by mathematical symbols. We see all these conservation of mass, conservation of the energy, conservation of the momentum has a similar form. Accumulation term, inlet input and output, and mathematical representation. So the big picture issue is the accounting concept. To count the extensive property, we must define three things. A system boundary. The first, we need to define what is our system boundary. Define what part of the universe is the interest. Let's say we have some reactor. Let's say we have some separation unit. We need to define first of all our system boundaries. Then second thing, we need to define what is extensive property. What is extensive property is depends on the system total mass or volume, total collection. Define what properties of interest. What we try to measure. Let's say we try to do the mass and the energy. Because of for the system, the mass is depends on the how big system you have, because when you increase your system size, your mass is increase. When you increase your system size, the inside total energy of your system is increased, so on. The third thing you need to define the time period, defined by the beginning and the end. Can be defined finite period, 1 hour, 1 day, on differential period rate of equation. We call this, if you define some finite period, we call this integral balance. But when you define some rate equation, some change of the system property, let's say extensive property respect to time, we call this differential period. About the system and the time period are differential, we call this PDs, partial differential equations. Let's say inside of your system, you try the measure, observe the temperature. If your temperature is change respect to your system position or the time, any position, we call these partial differential equations. So the conceptual accounting statement for finite time periods for integral case, accumulation of the extensive property in the system during the time period, let's say 1 day, 1 week, or 1 hour. So input of the extensive property in the system during this time period minus output of the extensive property from the system during the time period plus net generation of the extensive property in the system during the time period. Let's say you have some system. Let's say you have some city in a 1 year. You know how many people import this city and move in the city, and let's say you know how many people in a 1 year move out from the city, and let's say you know how many people died and born in the 1 year. We call first thing move in input, move out output, net generation mean the summation of the people born and people die. We call this net generation, because the generation mean it can be minus or positive, because if you lose the people by dying, we call this minus. If you gain the people by born, you call this the positive generation. And all these things give you net accumulation of an extensive property in your system. Then differential time period, accumulation of the rate of the extensive property in the system is equal the input rate. This time is the input, not the input of the extended property system during the time period. This called, we call this input rate. We call in here, let's say, in a 1 year, let's say 10,000 people move in. We call this just 10,000 people. But in here, we don't define any time period. This give you just rate. We call this, let's say, 1,000 per year. We call this some rate. Rate of extensive property of the system minus output rate of the extensive property from the system, and plus net generation rate of the extensive property in the system. Let's say 10,000 people per year die. Let's say 15,000 people per year is born. We call this the rate, not just in any finite time period. So where to now and where we are now and what is the next? Now we know conservation laws, accounting statements. We define first the system boundary, then we define what system properties we try to measure, we try to derive the equation to describe it. We call this first one is its macroscopic equation. This is algebra or ODs, and ordinary ordinary differential equation from the undergrad course. But in here, the second part, we call this continuum equation. The PD's partial differential equations involved. So in this course, in this book, basically for any system we define the boundaries of the system. We try to derive the continuum equation. This continuum equation is gonna have some PD's partial differential equation. That's mean any system property, let's say temperature, is gonna be dependent on the system position and or time. We call this partial differential equation, and in here the concept of the vectors and tensors and multivariable calculation is going to involve our analysis. So for example, in this course we are going to derive the mass conservation equations. Is for PDs, the representation of the PDs like this, and we will have this equation. For a laminar momentum, we will have this equation. For energy, we will have this equation. For second law, for entropy, we will have this equation. So the goal of this course, from the conceptual statements, derive this equation. Finally, what we are going to learn, basically, define our system and define our system properties, and define the time and drive all these three transport phenomena, and plus second law equation for any system is going to be our goal and our accomplish end of this course. So in summary, in the next following videos we will go over some mathematical concepts. It's going to be needed in this course to understand physical concepts, and actually we need very solid background in mathematics. Then go over some vector and tensor analysis and multivariable calculus overview. Then go start by chapter first and go over through the chapter 24 to understand all the basic concepts and the very important part of these books and part of transport phenomena during this course and studying by this Bird transport phenomena book. So I hope I see in the next videos, and see you in the next videos.